Let's talk about some notation for antiderivatives. Antidifferentiation is a fun word, but it's not very practical. We need some symbols that are going to tell us when we need an antiderivative. If I have a function, f of x, here's the symbol that tells me I want an antiderivative for this function, f of x. Here's what the rest of it looks like. The result of antidifferentiation is another function, and as we've seen, we need that constant. Some names for these things. I'm going to call this symbol an integral sign, an integral symbol. It's kind of, I'm having trouble writing and talking at the same time. It's kind of an elongated S, and the reason for that will become apparent eventually, not today, but sing. Nope. This is what I get when I try to talk and write at the same time. The letters just do what they want. So we're going to call that an integral sign. The function whose antiderivative we're going to try to find is the integrand. This dx, you might recognize that from taking derivatives, dy dx. This is telling us the variable of integration. This is not such a big deal. You might say, why do I need to know it's dx if I'm integrating with respect to x? Of course I am. It's a function of x. When you start talking about functions with more than one variable, that becomes critically important. But it still needs to be there now, even though our functions only have one variable. So it's telling us what's the variable that we're integrating with. The result, we've mentioned this word before, the result is the antiderivative. And actually, I guess I can sort of put that all the way over here. This plus c, we're going to call the constant of integration. So that's sort of the anatomy of the notation for this process. You might have guessed by the fact that integral integration is in here several times that another name for finding an antiderivative is integration. So antidifferentiation, integration, same thing. We might call this, we might pronounce this big F of x plus c is the indefinite integral, or the antiderivative of little f of x. I'm going to put that underneath here too. Indefinite integral. That doesn't mean we're not sure about it. We definitely are. You might be thinking, if there's an indefinite integral, doesn't that mean there should be a definite integral out there somewhere? And yes, there is, and we'll get to that, but not today. Today we're just talking about antiderivatives. So some notation that's telling us that we're looking for an antiderivative. So now I can write things like this and recognize that this symbol, the integral sign here, means I'm looking for an antiderivative. So I'm looking for a function whose antiderivative is the integrand, is this function in here. And hopefully you recognize that as the antiderivative of the inverse sine function. And there it is. We're used to thinking about it the other way. Here's the inverse sine of x. What's its derivative? the same question, just from the opposite end. Here's the derivative. What function is it the derivative of? The integral of secant x tangent x. Well, secant x tangent x is the derivative of the secant function. So the antiderivative of secant x tangent x is the secant function. Negative cosecant squared x. So all those trig functions, all the ones whose derivatives we know, we can now talk about with antiderivatives. What function has as its derivative negative cosecant squared x? That would be cotangent x. So when you see that integral sign, it means exactly the same thing as here's function, find its antiderivative.